In section 5.5, we're going to work on integration by substitution. This section here, and specifically as it pertains to moving on in the calculus sequence, it's going to be one of the most important sections we're going to cover in the second half of our class. We've already kind of seen some of the basic antiderivative rules for finding antiderivatives of elementary functions. If you remember kind of by an analogy, when we were doing our basic derivative rules, once we got to the chain rule, that widely opened up the class of functions that we could find derivatives of. Likewise, when we start to do integration by substitution, this is kind of like the inverse process of like taking an antiderivative of something that came from a chain rule. Essentially what we are looking for is we want to find the antiderivative of functions of the following form. Okay? So instead of having just a simple antiderivative of some function, little f of x dx, we could have had a function that was composed with another function. Let's suppose that function is g of x. And we want to find the antiderivative of this new function. Well, the basic idea is we're going to try to do a substitution that's going to reduce this more complicated and more involved antiderivative into a much, much simpler one that'll be a function of just maybe a simple variable u. To do this, essentially what you're looking for is you want to look inside of the integrand and you would like to see a function that's a composition such that the innermost function would also have its derivative present somewhere inside of the integrand. If that's the case, then we can make the following substitution. I'm going to let u be equal to g of x. I can then take the derivative or the differential of u, du, is going to be equal to the derivative of g we call g prime of x dx, and that will allow me to rewrite this integral as follows. It's going to be the antiderivative of f, and wherever I see the inside of f, that's equal to g of x, that's going to be my u, and then wherever I have a g prime of x dx, I can replace that with du. And under the substitution, I've gone from a more involved and complicated antiderivative into a basic one that's just a antiderivative of the function f, albeit of a function of u. Let's take a look at example 1. They want us to find the antiderivative of x squared plus 1 times 2x dx. Again, for us, we want to make a substitution here. What we're looking for in terms of our choice of u is we want to pick u that's a part of the integrand such that its derivative is also present. A lot of times, this will kind of involve letting u be something under an exponent. And for us, if I let u be the thing under this power of 2, let u be x squared plus 1, that's going to work out great because now when I calculate du is going to be 2x dx, and that's exactly what we see for the second part of this. So we can go ahead and we can rewrite our integral. It's going to look as follows. I have the antiderivative of something squared. Well, what is that thing squared? That's going to be u. And then in place of the 2x dx, I can put du. This is an antiderivative that we know how to do. The antiderivative of u squared du would be u to the third over 3 plus c. And then from there, remember, we started with an antiderivative in the variable x, so we would want to finish with an antiderivative in the variable x. And to do that, all you would need to do is to back substitute using your defining equation for u. U is equal to x squared plus 1. So everywhere I see a u at the end here, we can go ahead and replace it with x squared plus 1. So there we have it. The antiderivative of x squared plus 1 quantity squared 2x dx would be equal to x squared plus 1 to the third power divided by 3 plus c. We don't have to do this for all of them, but if you're curious, you can always go ahead and check this. If I take the derivative, I'm just going to rewrite it very briefly, of this answer, 1/3 x squared plus 1 cubed plus c, will that indeed give us the original integrand? Well, let's find out. We would have 1/3. To do the derivative, you'd have to use the chain rule, bring the power down, x squared plus 1, reduce the power by 1. From the chain rule, we need the derivative of the inside, which would be 2x. Derivative of a constant is 0. The 1/3s cancel, and sure enough, what we end up with is x squared plus 1 squared times 2x, which is what was in our original integrand. So we did find the correct antiderivative. In reviewing this problem briefly, let's just kind of make note of a few things. So what was the process? We look at the integrand, and immediately we would say, okay, I don't recognize that as being just a simple antiderivative. It's really kind of involved and has a lot of pieces that are there. So we want to do a U-substitution. The whole purpose of that U-substitution is to take this more complicated looking integral, or complicated looking antiderivative, and reduce it to a simpler one. What do I choose for my u? Well, I tried to let u be a portion of the function such that I also see its derivative present as well. I know the derivative of x squared plus 1 is 2x dx. So let u be the x squared plus 1. You then calculate your du, and then that allows us to make the substitution. After doing the substitution, this has transformed itself into the basic antiderivative of u squared du. We were then able to calculate that elementary antiderivative, and then finding our last answer by just simply doing a back substitution. Let's take a look at example 2. We want to find the antiderivative of 5e to the 5x dx. This is another one where we can do a u sub. It's not just the antiderivative of simple e to the x. It's the antiderivative of 5e to the 5x. So let's go ahead and let u, in this case, be the exponent of e. We know that with an exponential, it's the exponent that's typically the inside function of a composition. If u is equal to 5x, then du would be equal to 5 dx by taking derivatives of both sides. And what we see here is that this is now going to become e to the u, and the whole 5 and the dx multiplied together, those two will combine to give us our du. So under this substitution, we get the following. It's going to be the definite integral of e now raised to the u power du. This is an elementary antiderivative. We know that the antiderivative of e to the u is e to the u plus c. And then for our very last step, we just have to back substitute. Everywhere I see a u, we can replace it with 5x. So our final answer is e to the 5x plus c.